Hi all, welcome everybody to another technical session from Narrow Research. I'm Srijit here. So we are just continuing the diffusion coefficient calculation using AMS as a part of battery modeling uh, methodology. So previously we have done the optimization as well as the simulated annealings step to identify how to model an amorphous system. So we are just continuing the further analysis as well as the methodologies which we will cover in this diffusion coefficient calculation. Okay, so in AMS, as I said earlier, diffusion coefficient using the reactive force field engine are obtained from molecular dynamics simulations by analyzing the time evolution of atomic trajectories. So reactive force field is particularly suitable for diffusion studies in complex battery and materials systems because it allows bond breaking and formation, dynamic charge redistribution and simulations of large chemically reactive systems. So the diffusion coefficient is derived from either mean square displacement of mobile species or from velocity autocorrelation function. So both the cases are discussing here in this final tech video. So speaking about MSD of mobile phases, such as lithium or sodium or other ions using the Einstein relation, which looks long time atomic motion to macroscopic diffusion. So I'm not going into the depth of the theory. So as the first step, we need to prepare a periodic model of the system and select an appropriate reactive force field parameter set to compatible with the chemical elements involved. So MD simulations are typically performed under an NVT ensemble after proper equilibration. So while an initial NPT run may be used to relax the density if required. So due to the reactive nature um, of reactive force field, small time steps are necessary and sufficiently long simulation times, often hundreds of picoseconds, are essential to capture the diffusive behavior beyond the initial ballistic review. So this is actually the general input for that specific calculation. So obviously, let me show you what are the steps which we have undertaken. In this case, we have increased the number of steps to 1,10,000 and sample frequency to 5. The thermostat settings we have changed to 1,600 Kelvin for the temperature range and the damping constant to 100 femtosecond instead of picosecond. And once we run the calculation, before running the calculation, we select the respective force field from the force field library, lithium sulfate force field for this specific battery material. So it's a lithium sulfate material. So as once the simulation step is finished, let me show you that what is the exact output for this simulation. So this is actually the observed output. So you can see the simulation run after 1 lakh plus steps. So once the simulation is complete, the diffusion coefficient is calculated by evaluating the MSD of the selected species in AMS. This can be done directly using the built-in analysis tool where MSD versus time plots are generated and the linear region of the curve is fitted automatically to obtain the diffusion coefficient. So we can see both the things which I have just briefed. The diffusion coefficient, it's a linear curve. And from here we can generate this MSD. So I have followed that step only. So once I select MSD, it will display a small pop-up window like this where I have to set the frames from 2000 to 22,001 and 5000 is the MSD frame. Why I have selected this thing? So we are following this tutorial. So the maximum MSD frame to 5000 corresponding to 5000 into 1.25 femtosecond is equal to 6250 or 6250 femtoseconds. So that's why the maximum MSD frame is 5000 here in this step. The same case study only I have just performed here, and the observed output, the diffusion coefficient is around 3.50 meters square per second. So as per the tutorial case study, the observed value should be in the range of 3.09. So almost similar is the value which we got for diffusion coefficient through this MSD. So further, okay, for reliable diffusion coefficients, it is important to exclude the initial nonlinear part of MSD curve, average over many diffusing particles, and ensure statistical convergence by extending the simulation time if necessary. So the temperature-dependent MD simulation can be further used to extract activation energies through Arrhenius analysis. But overall, reactive force field based diffusion calculations in AMS provide a practical balance between the chemical realism and computational efficiency for studying ion transport in complex material systems. In the meantime, there is one more option that how we can do the diffusion coefficient, which can be calculated from molecular dynamics simulations using velocity autocorrelation function. So let me try that option also. So this is actually from mean square displacement. So let me see that how we can do autocorrelation function calculation. So here we need to follow the same steps. So 2000 to 22,001, and then I'm just changing to diffusion coefficient, lithium atoms. So ACF prime is also similar like 5000, and I'm just generating the ACF. So it will take few seconds to do the analysis, and once it is finished, we will get the respective plot for ACF. So it describes how velocity of the particle at a given time is correlated to its velocity at a later time. So it will be helpful for analyzing that particle velocity at a time t. Basically, it captures how long a particle remembers the initial direction of motion, providing the dynamical view of diffusion that complements the MSD approach. So in practice, this velocity autocorrelating function is calculated by averaging overall diffusing particles and multiple time organs along the MD trajectory. So it typically shows an initial rapid decay followed by small oscillations, especially in solids or dense liquids where the particle experience strong interaction with their surroundings. So numerical integration of velocity autocorrelation function up to the point where it fluctuates around 0 yields the diffusion coefficient. So that's the official outcome when we perform this calculation using autocorrelation function, velocity autocorrelation function. So it is taking a few more seconds, and this is actually the observed output for velocity autocorrelated function. So it is generating the graph, and as I said, so the respective observation you can see at the right hand side. Yeah. So this method is particularly useful for systems with limited long range diffusion or where MSD does not reach a clear linear regime within the accessible simulation times. However, it is sensitive to time step size and statistical noise. So high quality velocity data and adequate sampling are essential. So when carefully applied, velocity autocorrelation function based diffusion coefficient provide a valuable insight into the microscopic dynamics underlying the microscopic transport. So this is actually the official outcome of diffusion coefficient calculation using molecular dynamics in reactive force field engine with with the MSD as well as velocity autocorrelation function. So with that, I'm just winding up the session. So this is actually some videos which we have covered for battery modeling. The first methodology was diffusion coefficient. You know that it is not easy for us to cover the whole concept in 4 or 5 videos. It's a vast and wide application. The area has to cover in a depth way. So we will be coming back with new videos related to this area and the applications related to AMS in battery modeling and research. Thank you.